Okay, I've got a homework to send around. Assignment number 4. You can do question 1 right now. You can sit in lecture and do it if you want, although I don't think I'd recommend it given what we're going to cover in lecture. And I think by the end of lecture, you'll probably be able to do question 2, certainly by the end of Thursday. So I'll start this here. Thanks, June. Okay, 2 preliminary things before we get started. We're going to get started on mixed strategy Nash equilibria today. One announcement is that I'm going to have to leave campus right after class today, so I will not be having my normal office hours. My office hours this week are just going to be Thursday, and I'll make them a little bit longer to make up for that. On office hours this week will be 1:30 to 3, Thursday only. Okay. So don't come today, come see me on Thursday if you need to see me. The other thing I wanted to do just briefly at the beginning is several people have been asking about the distribution of midterm scores, so I'll put the distribution up on the board here. I'll say a little bit about that, say a little bit about how the midterm grade relates to your final course grade, or how it's worked out in the past, and I have a feeling it'll work out the same way this year. Okay, so the distribution of the midterm, 6 people got perfect scores on it. Including those 6 people, 70 and above, there were 44 tests in that category. So a large number of people doing very, very well on the exam. Scores of 60 to 69, there were 40 exams in that category. 50 to 59, 28 here. 40 to 49, 21 exams there. 30 to 39, 11 people here, and below 30, there were 7 exams. They should add up to a total of 151, unless I'm missing an exam or two. The mean score was slightly over 58. The median was 62. Okay? So this is a strange distribution of midterm scores overall. Midterm score distributions don't look like this for most classes, but every year it does look like this for PS30. The things that I think are unusual about this distribution is that there is a cluster of very high scores here, a very large number of very good exams, and then there's what I would call a very, very fat tail. There's more very low scores than you normally see in a political science midterm. And I'm drawing your attention to that because this part of the distribution doesn't show up in the final. Okay, the final exam scores are much more normal. What happens for the final exam is that a large number of people in the low categories, some of you guys who are sitting out there right now, and I'm sure you're not feeling very happy about your midterm scores, in past years, a number of you have really improved dramatically. Okay, so one thing that I think is unusual about PS30 is that we do tend to see a lot of improvement between the midterm and the final. And I think there's 3 reasons for that. One is the reason that I mentioned before the midterm. There was a lot of time pressure. Okay, even though most people did finish by the time was called, most people seemed to me just barely finished, and I'm sure some of you felt rushed. There will be less time pressure on the final. Okay, the 3 hours that you'll have, you'll be able to go at a slower pace, have more time to check your work. I think you'll find that very helpful. Second reason why there's usually such a big improvement from the midterm to the final is I'm guessing for many of you, you're not used to having that kind of exam. Okay, that it's not like a typical poli-sci exam. You're not writing essays. You're not demonstrating that you've mastered a large amount of material that you've been given to read, which is something that is more typical in a political science class. Okay, so if this was the first time you took an exam like this, where you have this task of translating a problem into an analytic framework, analyzing it, and then interpreting the answer, the first time is hard, and I bet you learned a lot from the midterm. Okay, so you're just going to be better at this kind of test on the final exam. The third thing is you're going to know a lot more game theory by the end of it, and even though the topics that we're covering after the midterm are different, there's a lot of reinforcement. Okay, so I think you're going to feel more comfortable with it. So again, let me emphasize, in the past, people in this range have done much, much better on the final exam. I should also say that in the past, I hope this doesn't happen this year, but every year in the past, there have been a couple of people who've really nailed the midterm and I think have gotten the wrong signal from that. There's always a couple of people who do really well on the midterm and surprisingly poorly on the final. I've never actually known what's going on in those cases. I strongly suspect that there might have been some false confidence from the midterm. Okay. Now, I'm not taking back what I said a minute ago. You guys are going to know a lot more game theory by the time the exam comes. But let me say something else on the other side. The hardest game theory is the stuff after the midterm. Okay, that's sort of it's a naturally cumulative subject, and in particular, the topic that we're starting this week, mixed strategies, is a topic that most people find weird. It's not this week would be a particularly bad one to coast on. Okay. One other question that came up in the context of asking about the midterm distribution is people asked me would there be a curve for the test? I don't really curve the exam. I mean, the numeric score goes into your final point score for the course. So the more relevant question is, how do I decide letter grades from the course? And so I'll tell you how I do that. What I do is I look at what the distribution of grades would be with what I think of as the standard curve. 97.5 and above is an A, 92.5 is an A plus, 92.5 and above is an A, et cetera. The kind of the standard non-curve, that assignment of letter grades. And I also look at what a curve would be. 30%, and the top 30% getting an A or something like that. And I choose the distribution that would advantage you guys. Most years, there's not a lot of difference. Okay? The last few years, the standard cut points, 97.5, 92.5, 90, 87, all of those, have given about the same as what you would do with a relative curve, have given about 30% A's, 30% B's. Okay? So what I would do is, if I don't think there's enough A's based on the curve, I'll take it down. I'll take the cut points down so that basically I would adjust for what I would perceive to be an unusually hard final exam. The curve won't hurt you, though. If I mess up and give you too easy in a final exam and 40% of you get 95 and above, you guys will all get A's. Okay? So that's how that will go. Okay. So to get to that happy outcome where large fractions of you are getting very high scores, I'd like to have that happen. Let's take a look at a game for that. Okay, so we're going to start a new simultaneous game today. The game we're going to start is Cops and Robbers. Okay, so it's a two-strategy, two-player game, just like the ones that we were analyzing last week. And we're going to let the cops be the row player, the robbers be the column player. Okay. This game's going to be a little bit different than most of the ones we were looking at last week. And most of the ones we were looking at last week, the players' strategies and payoffs were symmetric. Okay. They both have the same choices to make. Here, choices are different. Okay. The cops' choices are, they could be on the beat, driving around, looking for criminals, doing their thing, or they can be in the donut shop, sitting on the bench, flirting with the waitress, eating some donuts. The robbers can be at work. They can be out there robbing people, or they can be at home. Okay? So some similarity to their strategies, but not exactly the same thing, and the payoffs are not going to be symmetric. Okay. From the cops' point of view, I'm going to do all the cops' payoffs, and then I'll do all the robbers' payoffs. From the cops' point of view, this is the best outcome. Okay? The robbers are at home. They're not creating any trouble. There is no trouble. I'm in the donut shop. It's comfortable. It's warm. I like that. That gives me a payoff of 5. Okay? The worst thing, though, is I'm in the donut shop. The robbers are at work. There's a lot of crime on my beat, and boy, I'm in trouble with my supervisor. Okay. In between that, if I'm on the beat and the robbers are at work, well, you know, I became a cop because I like catching bad guys. That gives me a pretty good payoff. Justice is being done. I'm apprehending those robbers while they're committing the crime, so I'm getting a payoff of 2. If I'm on the beat and the robbers are not active, okay, they're home, there's no crime going on, it's kind of boring, I'm tired of my partner, we're driving around, okay, so that's not a very good payoff for me, but it's still much better than for me to be slacking off eating donuts while there's crime going on my watch. All right, so those represent the cops' payoffs. From the robber's point of view, I'm a robber. I want to rob people, I want to get their stuff, I want to make some money out of it, and I don't want to have to deal with the cops. The robbers like this scenario. The cops are in the donut shop, the robbers are out there committing crimes, they're getting a high payoff there. The worst thing, from my point of view, if I'm the robber, is I go out, I'm trying to commit my crimes, and the cops catch me. Oh boy, that's bad. Okay, that's bad payoff for me. if I'm at home, this is something else that I haven't done, I just want to show you, you can do this. If I'm at home and I'm the robber, I don't care what the cops do. They can be on the beat, they can be at the donut shop, doesn't affect my payoff at all. Okay? So this kind of strategic situation happens sometimes where one player's payoffs are affected by the other player's decision in some cases, but not in others. Okay? That doesn't affect how we set up the game at all. It's just a normal case. We just represent it by having the payoffs be the same. Okay. So what's the interesting thing about this game? If we use the processes that we went through last week, first thing we do is we look to see if either player has a dominant strategy. Okay, well, the robbers obviously don't have a dominant strategy. Depending on what the cops do, going out and being at work is either much worse for them or much better for them. So no dominant strategy there. And the same for the cops. Okay, if the robbers are at work, the cops would rather be on the beat. If the robbers are at home, the cops would rather be in the donut shop. So thing one. No dominant strategy for either player. And because this is just a two-strategy game, no dominated strategies either. So any of the iterated dominance things are not going to work. Dominant or dominated strategies. Okay, so the next step that I taught you last week to go through is to just go through and look at each cell and ask yourself, in each of the possible cells, is there a cell where neither player would have regrets? Okay. Well, if we're in this cell, okay, the robbers are at work and the cops are on the beat, does either player have regrets? Yeah. Who has regrets in this cell? The robbers. Okay. Given that the cops are on the beat, the robbers wish they'd stayed home. Okay. They don't want to be taken away in the paddy wagon. All right. So this is not Nash equilibrium. In order for it to be a Nash equilibrium, both players have to have the highest payoff they can get given the other player's choice. So the column player's payoff has to be the highest given the row we're in, and the row player's payoff has to be the highest given the column we're in. Okay? If either player has regrets, it's not a Nash equilibrium. So maybe this is. Okay? So who's got regrets here? Cops. Robbers are at home. I could have been in the donut shop. Okay? Cops have regrets here. Here, cops are in the donut shop. The robbers are at home. You know, the robbers need to make a living. They could be out there breaking into cars, stealing things. They could do that. And finally, we get to this cell. In this cell, if the robbers are at work and the cops are in the donut shop again, the cops have regrets. Okay? So that's bringing us to point A in the outline, and you'll notice I have a question mark here. Okay? It looks like there's no Nash equilibrium in the sense of the Nash equilibrium we were looking at last week. Okay? What we're going to do this week is we're going to say there is no Nash equilibrium in pure strategies. Okay? What does that mean? No Nash equilibrium where both players clearly do the same thing. Okay? No Nash equilibrium in which players make certain predictable choices. Okay? That by itself is worth knowing. Okay, it's worth knowing in this game that it is a mistake to be predictable. Okay, when you find a game that has no Nash equilibrium in pure strategies, that's what it's telling you. Okay, that if the players play predictably, they're going to have regrets. Okay. That if in any of the predictable situations, one of the players is going to regret what they're doing. Okay? So that's moving us toward the idea of mixed strategies. Okay, so let's just say what a mixed strategy is. A mixed strategy is a probability. I'm not spelling that right. Too many syllables in that word. Probability that each choice is made. Okay. In fact, the probability is between 0 and 1. Okay, what do I mean? It's not certain. Okay, if I'm playing a mixed strategy, I am randomizing. Okay, sometimes you'll hear it put that way. I am making a random choice. I'm rolling dice. Okay, I'm playing that way that we thought about nature playing in the sequential games part of the course. Okay, and the rolling dice is one way, one concrete way to think about randomizing, but a way that is better, that I'm going to encourage you to think concretely about. I had a prop I wanted to bring in today, but I didn't bring it in. I'll have to draw it on the board. The way to think about choosing at random is to think about spinning a spinner. Okay? Like when you were a kid, if you played a game like Twister or something like that, where you spun the needle, okay, and if it landed on the elbow in a yellow square, you had to put your elbow on a yellow square, something like that. What you're doing is you're spinning a spinner, and this is a more useful way to think of it because the spinner's on a circle, and what fraction of the circle is shaded different colors is going to tell you the probability you're on the beat or you're in the donut shop or you're at work or you're at home. Okay, the spinner analogy is a better one because it allows us to think about all possible probabilities. Okay, something like this would be a 50-50 probability. Something like this would be a 25% probability of one strategy, a 75% probability of another. Thinking about the spinner being colored different ways allows us to think of all the possible probabilities the cops could assign to being on the beat, the robbers could assign to being at work. Okay. So, again, I'm hoping that I'm doing one step backward, two step forwards, doing some repeating, but also moving the idea forward here. When we don't have a Nash equilibrium in pure strategies, that's telling us something about equilibrium behavior. Equilibrium behavior cannot be predictable. If your behavior is predictable, you will have regrets. Okay? The other thing about, and what we're going to be calculating when we find a mixed strategy equilibrium, is that in order for both players to be in equilibrium, in order for neither player to regret making a choice they care about by spinning a spinner, in order for that to happen, the probabilities have to be specific values. Not just any probability will work. Okay? And the probabilities are going to depend on the payoffs in the game. Okay? Given the payoffs in a game, if you're giving too much weight, too much probability to one strategy, you might not be in equilibrium. Okay? Let me step out of the basic narrative for a minute and make a comment on this. This is one of the reasons why mixed strategy, Nash equilibrium, I said at the beginning of the class, is kind of a hard topic. It's not very intuitive. So what we've gone over the course of the last 6 weeks, we've gone from the rollback process, which I think most of you guys found sort of sensible, that if you really care about the long-term consequences, you look ahead, you reason backwards. That sounds like a process that somebody would go through in their head when they're making a strategic decision. Last week already, you may have felt that sense starting to blur a little bit when we were talking about the multiple equilibria. Okay, battle of the sexes, these assurance games where you can be in equilibrium. Okay, we could both be at the good equilibrium in the assurance game. We can both be in the equilibrium where we clean the apartment. But there's that other equilibrium when we both don't clean too, and how do you know, and how do you try to figure it out? It's less clear there. Okay, so simultaneous games are less helpful in teaching us what to do in a specific situation. They can teach us some things not to do, but if you want to know what to do in a specific strategic situation that has multiple equilibria, you have to know something about what equilibrium is more focal. Okay, you have to know something that game theory can't tell us. Now we're getting even further away from something that can be applied. Okay? The applied message of games without pure strategy, Nash equilibria, is that you don't want to be predictable. And I am, throughout this week and next week, going to spin out some lessons from that about how to be unpredictable. Okay? But our analysis of mixed strategy equilibria is taking us as far as we're going to get from a process that goes on in people's heads. Okay? So what I'm saying is I don't really think people are spinning these spinners. Okay? In fact, you'll even see that they can't really gain by doing so. So mixed strategy equilibria is something that helps us understand situations. It's helpful for understanding how people make the choices that they do. It's less helpful for telling you what to do in a specific situation. Okay? That's just the fact. Right? Again, it's telling you what not to do. Don't be predictable, but that's about it. Okay. All right. So now back into the main narrative. What I'm going to do is I'm going to go through the process of finding the mixed strategy Nash equilibrium. And I'm going to be doing more than one example of this over the course of the week. But during my first example, I'm going to really try to give you the why of the explanation as well as just the cookbook side of it. Okay, so I'm going to try and show you some steps to go through, but I hope I'm going to convey the reason why the steps work. All right. So I'm going to clean up the blue. And while I'm doing this, I'm going to elaborate on the first point on the outline there. Okay? In order for either player to be okay with this idea of making a choice by spinning a spinner, making a choice completely at random, the only way they are going to be willing to do that is if they are indifferent between either pure strategy. I'm the cops. The only way I am willing to make a random choice between being on the beat and being in the donut shop is if the payoff I get from being on the beat and being in the donut shop is exactly the same. If what I expect to get from being on the beat is different, what my expected payoff is different than what my payoff is in the donut shop, I should go with the pure strategy that gives me the higher payoff, right? If what I expect to get from being on the beat, balancing the probability that the robbers are going to be at work or at home, that's why it's an expected payoff here, expected utility. If it's different, I should go with my pure strategy. The only way I'm willing to spin a spinner is if what I get from making either choice is exactly the same. Okay, that is the key insight to finding mixed strategy equilibrium. That I want to get a different color to augment the outline here. Both players must be indifferent between their pure strategies. Okay. And you're thinking, well, how can I be indifferent between 2, -5, 1, and 5? They're different numbers. Well, you're the cops. You only get to choose a combination of 2 and 1 and -5 and -5. The way you could be indifferent is there could be a probability of the robbers being in this column or that column that would make the expected values the same. That's where we're going to go. Okay? So both players must be indifferent between their pure strategies. That means that the expected payoff from pure strategies are the same. If you're wondering what happened to point A, somehow I thought I was going to cover it first, but I'm going to cover it in a minute. Okay, so I'm emphasizing this point. You'll see point A in just a second. Okay. So how, I'm the COPS, how can I be indifferent between my pure strategies? I can be indifferent because they're both expected payoffs depending on the probability that the robbers are at work. Okay? That's going to bring me to part A. If I'm the COPS, my expected utility is a function of the robber's probability. I'll write that in. The COPS expected utility is a function of the robber's probability. What does that mean? Let's start over here. Okay. We don't know what the probability is that the robbers are going to be at work or at home. We know it's going to be between 0 or 1. Okay? We know that because if it's 0, the robbers are going to be predictably at home, and if it's 1, they're going to be completely at work. And we know that they don't want to be predictable. Okay, so we know that a probability of 0 or 1 for the robbers is not going to be in equilibrium. Okay, but we don't know what exactly the probability is, so let's let it be a variable. Okay, let Q equal the probability the robbers are at work. Okay. Now go back to part A here. Q is the robber's probability, and it determines the COPS expected payoffs, right? Let's see how that goes. Okay. So the expected utility of the COPS, that's how I'm going to write the expected payoffs. Okay. The expected utility of the COPS from being on the beat. Oh, it's an expected value. We're going to calculate it just like we calculated the expected values before. It's what I get from being on the beat when the robbers are at work, that's 2, times the probability that the robbers are at work, plus what I get from being on the beat when the robbers are at home, that's 1, times what? 1 minus Q, yes. Okay. Here's point A. The expected utility of my pure strategy depends on the other player's probability. Okay? So let's pretty that up a bit, because we're going to need it in a minute. So 2Q plus 1 minus Q, that sounds like Q plus 1. Check me on this. Sounds okay? All right. So this is the expected utility to the COPS of being on the beat. And what I'm saying is it has to be the same as the expected utility to the COPS of being in the donut shop. So I'm calculating the expected utility of each pure strategy for one player, and it's a function of the other player's probability. Okay? I've done it for being on the beat. For the donut shop, it's the same story. My expected payoff from being in the donut shop is the payoff I get from being in the donut shop when the robbers are at work. That's -5 times the probability that the robbers are at work, plus the payoff that I get from being in the donut shop when the robbers are at home times the probability that the robbers are at home. Okay? Just as we did when we were using probability to solve nature nodes, we were using expected values to solve nature nodes, the probabilities always have to add up to 1. Okay? When you're balancing different outcomes, if the probabilities don't add up to 1, you've made a mistake. Okay, so let's pretty that up as well. -5Q plus 5 minus 5Q sounds like 5 minus 10Q. Does that sound right to you guys? No. Yep. Good. Lose the spinner here. Okay. So, where am I in my outline? Point B here is the main logical point that allows us to calculate mixed strategy equilibrium, that both players have to be indifferent between their pure strategies. Each pure strategy has to give me the same expected payoff. Point A reminds me of how to calculate the expected payoffs from a pure strategy, that it's going to be a function of the other player's probability. So I've done that. Last thing in finding 1/2 of the mixed strategy Nash equilibrium is to put those two expressions together and find the robber's mixing probability, the robber's probability of going to work that makes the cops indifferent between their two strategies. Okay, so that means setting this expression equal to this and solving for Q. The algebra is not hard. The wind-up, the logic of remembering what to do is what can be tricky here. Okay, so the cops are indifferent. Okay, they get the same payoff from, I'll write out the two pure strategies, from being on the beat or in the donut shop when Q plus 1, what I expect to get from being on the beat, equals 5 minus 10Q. Okay, so let's solve that. That says 11Q equals 4. Q equals 4 11ths. This is half of the mixed strategy equilibrium, half of what we're looking for. This tells us the robber's equilibrium probability of being at work. Why do I call it the equilibrium probability is the question, and I'm pausing for a minute to see if I can give a better answer than because that's what it's called, but that's sort of what, it's just the phrase. Here's a way of thinking about it. What we're doing here, sure, that's okay. What we're doing right now is the process of finding a mixed strategy equilibrium. And so the broader question here is, what are we looking for when we look for a mixed strategy Nash equilibrium? Okay, we're not looking for a pair of strategies anymore such that neither player will regret their choice given the other player's choice, because we know that there isn't one. Okay? What we are looking for is a probability distribution over each player's strategies such that neither player will have regrets given the other player's probability distribution. Okay. So what we're looking for when we're looking for a mixed strategy Nash equilibrium, I'm going to say it in more ordinary language now, is we're looking for a probability for each pair. Okay? We are looking for a probability that the robbers are at work. We found that. We're also going to look for a probability that the cops are on the beat. And those two probabilities will be in equilibrium if, given the other player's probability, neither player regrets their own probability, regrets making a random choice. Okay? So now I think I've talked myself around to a more coherent answer to Elaine's question, the equilibrium probability here is the analog to an equilibrium strategy in the pure strategy Nash equilibrium that we've found so far. Okay? In a very general sense, those pure strategy Nash equilibrium, you could think of them as probabilities too, but it just puts 0 and 1 probabilities on the different strategies. When the probabilities are between 0 and 1, that's when we really have to emphasize that we're looking for equilibrium in mixed strategies. Okay. All right. So what I'm going to do is I'm going to copy what we've got so far over here, and then I'll erase to find the other half of the mixed strategy Nash. Okay, so want Q equals the probability robbers at work. It's very important when you're doing your homework and on exams to be clear which strategy you're representing with the variable, which is going to be 1 minus Q. Okay? You'll get the same answer in terms of interpretation if you let Q be the probability of being at home and 1 minus Q being the probability of being at work. Okay? You'd find that the probability of being at home would be 7/11ths, and the probability of being at work would be 4/11ths. You'll get the same numbers, but in order to keep track of what goes with what, I highly recommend writing it out just like this. Okay, so we want that, and we want P, the probability that the cops are on the beat here. Okay? And we want these probabilities to be the numbers that will allow neither player to have regrets. Okay? Okay. And what we found so far is that if Q equals 4/11ths, the cops are not going to regret making a random choice. What's strange about the mixed strategy Nash equilibrium, what's different than what we've done before, is we're calculating one player's probability based on the other player's payoffs. Okay, and that is just a fact about mixed strategies, a fact that we're going to be elaborating on during the week. Okay, with pure strategies, in order to find my equilibrium strategy, we looked at my payoffs. That seemed reasonable. Mixed strategies, we're down the rabbit hole. In order to find my probability, my equilibrium probability, we have to look at your payoffs and vice versa. So now we're going to do the vice versa. So I'm looking for P. I'm looking for the equilibrium probability, the analog of the equilibrium strategy of the cops, the probability that they're on the beat. In order to find that, what I'm going to have to do is I'm going to have to find the value of P that makes the robbers indifferent. Makes them indifferent between their pure strategies, but I'm not going to write that whole thing. Okay? Find the value of P that makes the robbers indifferent. So what I have to do now is I have to calculate the expected utility to the robbers now of each of their pure strategies, and it's going to depend on P, just as the cops' expected utility depended on Q. Okay? So if I'm the robber, we need to say what's the expected utility of here. My expected utility of being at work is the payoff I get when I'm at work and the cops are on the beat. That's -5 times P, which I've defined to be the probability the cops are on the beat, plus the payoff I get if I'm at work and the cops are in the donut shop times the probability that the cops are in the donut shop. Because if they're on the beat with probability p, they have to be in the donut shop with probability 1 minus p. Okay, and making that look nice, it looks like it's 5 minus 10p. So that's what I expect to get from one of my pure strategies. The other pure strategy is actually easier in this case. The expected utility of the robber from being at home. Here it doesn't matter, okay? I'm the robber, I'm at home, I don't care what the cops are doing. I get a 0 either way. If I was working and I didn't see the big picture and I said, okay, it's 0 times p plus 0 times 1 minus p and just cranked it out like that, I'd still get the right answer. It wouldn't be a problem, but I don't have to. I don't have to do that. So the value of p that makes them indifferent is the value that makes the expected utility from being at work exactly equal to the expected utility from being at home. It's 5 minus 10p equals 0. Sounds like p equals 1/2. Okay. Now we're done. This is the mixed strategy Nash equilibrium. Okay. This is the probability distribution for each player over their strategies. I know that's a mouthful, okay, but all it means is the probability that the cops are choosing one strategy, the probability that the robbers are choosing another strategy. And with these probabilities, neither player is going to regret the choices that they made. Neither player can do better by making a different choice. Okay? Neither player can do better by playing a pure strategy, and neither player can do better by picking a different mixing probability. Okay? So we've got these probabilities. We are in equilibrium. Okay? Concretely, what we're thinking here is the mixed strategy equilibrium tells the cops and robbers what spinners they should be spinning. Okay? So it's a spinner for each player, the cop spinner, and the robber's spinner. What we've found is we've said, okay, cops, you've got an easy spinner. It's half-half. Okay? It's the shaded side, you do donuts. If it's the white side on the beat, the cops could flip a coin too because their mixing probability worked out to be 1/2. For the robbers, it's a little bit trickier. We have to have something about like this, I guess. 4/11 of being at work and 7/11 of being at home. All right. So, yeah. What I think I want to talk about now is, I'm getting really efficient. Last week I was surprised to get to the end of my outline because I hadn't been doing that. Today might be the first day that I go beyond it. And what I think I'm going to do is, actually what I think I'm going to do is pause for questions for a minute. Okay. No questions. And time will tell whether that's because it's so obvious or it's too weird to even ask questions about. Okay, let me actually say something about the mixed strategy problem on the back of your your homework. Okay, so you've got one standard homework problem here, question 1 with 5 different scenarios, scenario A through E, and at the beginning, numbered questions that I want you to answer for all the scenarios. That's all about stuff from last week, okay? You guys fine with that? It's all asking you about pure strategy Nash equilibrium. I think the only thing that you wouldn't have known about this if I'd handed it out on last Thursday is you wouldn't have known what a pure strategy was because we hadn't made the distinction yet. But just let me emphasize again, a pure strategy is when you pick one thing for sure. The natural meaning of strategy that we've been using so far. The second part is a set more of little drill problems. No stories here, just matrices with numbers to give you practice finding both the pure strategy Nash equilibria and the mixed strategy Nash equilibria. Okay, so you can start doing those right now and get in the groove of doing what I did here, of using one player's probability as a variable to set the other player's expected payoffs equal, okay, and then using that relationship to indeed find the equilibrium probability for the first player, and then switch the roles and do it again. When you're looking for a mixed strategy equilibrium, you're looking for a probability for each player. Okay. Another thing then to think about is what happens in equilibrium here. Yeah, Elaine.
I understand how there won't be there can be no pure strategy Nash equilibrium, but how can there be no mixed strategy Nash equilibrium if we solve it this way? You're always going to end up with some probabilities, right?
Elaine asks, how can there be no mixed strategy Nash equilibrium? And I'm going to give sort of a short and a long answer to that. In the context of that question, saying no mixed strategy equilibrium, what I mean is no equilibrium where there's some probability that each strategy is played. If you get a probability of 1 for one of the strategies, I would not, most people would not consider that a mixed strategy Nash equilibrium. That would be a pure strategy Nash equilibrium. Okay. But it actually begs a question that I think is worth considering right now. I'm thinking about what to do. I don't want to start what I think of as kind of another big thing right now, but this is a good point for me to address right now. How can you know if a game doesn't have any mixed strategy equilibrium in that sense? So let's look at one, and we'll see what happens here. Okay. And lo and behold, here's one. I know my friends in the back don't like it if I use this green for important stuff. It's going to be a prisoner's dilemma. And while I'm doing the calculation part, you guys might just even be thinking to yourself logically how we might know that there's no mixed strategy Nash equilibrium in the prisoner's dilemma. Okay, so it's player A can defect or cooperate. Player B, defect or cooperate. Payoffs will be -2, 2, -5, 0. This looks like my same old payoffs here. 0, -5, -1, -1. Okay, just reminding ourselves, is this a prisoner's dilemma? The role player's dominant strategy is to defect, right? -2 is better than -5, and 0 is better than 1. Column player, same story. They both have a dominant strategy to defect. They're both worse off than if they both play the other strategy. The highest payoff for each player is when they defect and their partner cooperates, and the lowest is the sucker payoff. So yeah, it's a prisoner's dilemma. Okay, so let's just get to work on this using the mixed strategy recipe. Okay, so what we would be looking for a mixed strategy Nash equilibrium would be a probability Q, probability that A defects, and P, the probability B defects. You might suspect that these are going to be related to each other since the game's so symmetric in this case. So if I want to find Q, the probability that A defects, what I have to do is I have to find the value of Q that makes who? That makes B indifferent, right? Q is A's probability. Q is going to affect B's payoff. So the expected utility to B of defect is going to be what I get, I'm B, from defecting if A defects, that's -2, times Q, which I've just defined as the probability that A defects, plus what I get if A cooperates, what I get, I'm B, okay, got to look at the column players payoff. Okay, so that equals -2Q. Fine. The expected utility to B of cooperating is what I get if I cooperate and A defects, -5, times the probability that A defects, that's Q, plus what I get if I cooperate and A cooperates, times the probability that A cooperates, that's 1 minus Q, so I get -5 Q plus a Q, that sounds like -4 Q minus 1. Does that look right, guys? I'm getting past the witching hour when algebra skills, such as they are, deteriorate. Okay. So the value of Q that makes B indifferent is going to be the value of Q such that -2Q equals -4Q minus 1. 2Q equals 4Q plus 1. Okay, so bring this over, I'll get -2Q equals 1. Q equals -1/2. Did I make a mistake this time? I didn't. I don't think I did. This is a case where what this unreasonable result is telling us is that there is no value of Q that makes sense as a probability that would make B indifferent. Okay? So if you're looking at those games on the homework and you get a result like this where the probability doesn't make sense. Why doesn't it make sense? It's not between 0 and 1. Not okay as a probability. Yes, go back and check your work. You might have made a mistake. It's possible. But you might not have made a mistake, and it might be the game telling you something. Okay? This is a game where the players are never going to randomize. And actually, any game with a dominant strategy is never going to have a mixed strategy equilibrium. If you have a dominant strategy, it's a dominant strategy. It's always better, no matter what the other player does. There's not going to be anything the other player can do to make you indifferent between your dominant and your dominated strategy, right? That's what it means to be a dominant strategy. So games with dominant strategies are one example of games that never have mixed strategy Nash equilibrium. Okay? So you might be wondering, how do things shake out here? Let's sort of do a table here of pure strategy, Nash equilibria, yes, no, mixed strategy, yes, no. I'll be doing some examples here, what we've seen is that the prisoner's dilemma, I'm doing a 2x2, but it's not a game matrix. It's just, categories here, the way you'd have a 2x2 table in statistics here. There are games like the prisoner's dilemma that do have a pure strategy Nash equilibrium, don't have a mixed strategy Nash equilibrium. There are games like cops and robbers that don't have a pure strategy equilibrium that do have a mixed strategy equilibrium. There are some games that have both. Assurance, Battle of the Sexes. I might do an example along these lines for you. Question is, are there games that have neither? Okay, and there's sort of a, well, what's the answer here? Empty as long as the set of strategies is finite. Okay? So what am I saying here? As long as the set of things you can choose is has a finite number of things in it. Okay? You can't choose from an infinite set of things. You're guaranteed to have one type of Nash equilibrium. Okay? You might have both, okay, or you might just have mixed strategies, you might just have pure strategies. So the paper that John Nash published that earned him the ability to put his name in Nash equilibrium was a paper proving that this was true. Okay, so that proof is what made the idea of Nash equilibrium seem so appealing, that as long as you have a finite set of strategies, both players have a finite set of strategies, one type of Nash equilibrium will exist. We can always find one. The question is how big a qualification this is. The way to understand these kind of qualifications is to ask yourself, what would be a case where this wouldn't be true? Any thoughts on that? Where the set of strategies that you would be choosing from would be infinite. Okay. It's kind of a hard thing to think of on your own. I think I was really wondering if anybody had it in the class. If your strategies involve choosing a point on the line. Okay, and we use these kind of games in political science a lot. Games where you're using the real number line to represent, say, a candidate choosing their position. Am I going to be, far left or far right or middle of the road? And if you really think that I could choose any point on this line, then my strategy space is finite. And some of these games of political competition, of finding your position on a line and my opponent finding their position on a line, will fail to have Nash equilibrium. Okay. This stuff, all this stuff is beyond PS30, but I think it does sort of help you see in context. So in PS30, we are interested in these cases. If you are interested in this kind of issue, like big, broad classes of games where you can or cannot find Nash equilibria, the math department game theory class, that's something that they would make much of. I think it's Math 165, so that would be a course to check out for that. Okay. All right, so the other thing I want to do today is, do I still have Cops and Robbers here? Yes, I do, hooray, because I'm not done with it. Okay. I'm going to go back to Cops and Robbers, and I want to think about what the prediction would be here, right? I'm now mapping this game that has a different kind of equilibrium, different in some ways but the same in others, okay? The mixed strategy equilibria are different because of what we are looking for. When we're looking for mixed strategy equilibria, we are looking for a probability for each player. That's what's different, such that neither has regrets given what the other is doing. That's what's the same. Okay? The Nash equilibrium idea always has this idea of me not having regrets given what you did, and you not having regrets, you not having a better choice given what I did. Okay? Just in this case, we're allowing both of us to choose randomly. Okay? But randomly doesn't mean any old choice. Okay? If in cops and robbers, you're the robbers and the cops are choosing randomly, but they're choosing a different probability than p equals 1/2. Okay? If the cops are, we're going to go over here and think about something that would be out of equilibrium. Suppose p equals 1/4. Okay, we're getting some kind of lazy cops here. They really don't like being on the beat. They want to be in the donut shop. And let's say that's their mixing probability. They're choosing at random. Question is, I'm the robbers. Am I going to be willing to choose at random as well? Well, let's see. Expected utility of the robbers of being at work now is -5 times p. Okay, -5 is what I get from being at work when the cops are on the beat, and I'm saying in this out of equilibrium scenario, I'm saying that the probability is 1/4 plus 5 times 3/4. Okay, that's what I get if I'm at work, I'm the robbers, and the cops are on the beat, multiplied by the probability, the cops are in the donut shop, I get the good payoff, and the probability that the cops are in the donut shop. Okay, so this is -5 plus 15/4, 10/4, or 5/2. Okay, this is my expected utility. I'm the robbers. Okay. Am I going to spin my spinner? No. I'm not going to choose randomly. If I can get an expected payoff of 5/2 from going to work and a guarantee of 0 from staying home, I'm going to work. Okay? And then if I'm going to work, we can't be in equilibrium. Because if I'm at work and whatever cell the cops, when they spin their spinner, ends up in, one of us is going to have regrets. Okay? If I'm at work, which is what I would prefer to do, and the cop spinner tells them to be on the beat, well, I'll have made an ex post mistake. But if the cops are in the donut shop, the cops are going to be unhappy. Okay? So I'm not indifferent. If the cops are playing the strategy, robbers will do better by playing a pure strategy. So again, to emphasize the interpretation here, in a mixed strategy Nash equilibrium, both players are playing randomly, and neither can do better by being predictable. But by randomly, I mean a specific probability. Okay, in mixed strategy equilibrium, there's usually there's a specific probability for each player that will bring the system into equilibrium. What's weird about it, what's less intuitive than about pure strategy Nash equilibrium, is that it's the robber's probability that makes the cops willing to randomize. And it's the cop's probability that makes the robbers willing to randomize. Okay. So if the cops change their probability, if the cops, instead of their equilibrium probability of 1/2, the cops pick a different equilibrium probability, it actually doesn't affect the cop's payoff. Okay, so if the cops make a mistake, it doesn't hurt them. And that's what makes mixed strategy equilibrium, in my mind, stranger than pure strategy equilibrium. But it brings the system out of equilibrium by making the robbers no longer willing to play the mixed strategy, and vice versa. If the robbers get it wrong and they mix with probability 9/11 instead of 4/11, with probability 9/11, they go to work, it doesn't affect their payoff. The reason why it doesn't affect their payoff is that if we change just the robber's probability but leave the cop's probability the same, okay, the robbers are still indifferent between their two pure strategies. Right? The robbers, as long as p equals 1/2, the robbers are getting the same payoff from being at work as they are at home. So if I change q, I'm not changing the robbers' expected payoff at all, okay? Because what they're getting is the same in either case, okay? As long as p is in equilibrium. All right, so that point that I'm ending with, I'm going to say some more things about, but also approach from a different point of view.